Fluid statics is the study of the mechanical behavior of fluids that are at rest. Of course, the molecules within any fluid, or even solid, are never at rest. The molecules are constantly moving, and bumping into each other, or into the container's walls. Hence the state of rest that we describe here is not applicable on the atomic scale. But it can be achieved on the macro scale, if the average velocity of a very large number of molecules of the fluid is zero, with respect to the container within which they are placed. We conduct an experiment, in which we use a solid cylinder, and a cylindrical container filled with water, and equipped with a piston. The weight is placed on top of the solid cylinder, and a similar weight is placed on top of the liquid container's piston. Both the liquid and the solid columns have the same cross-sectional areas, as we have seen before, in the solid mechanics section. When a weight exerts a normal force F on a solid column, the normal compressive stress within the material is equal to the force divided by the cross-sectional area of the column. For simplicity, the liquid container's piston is assumed to be of negligible mass. In this case, assuming the liquid is incompressible, the pressure within the liquid just underneath the piston is equal to the force exerted by the weight divided by the cross-sectional area of the liquid column. Unlike force, which is a vector, and acts in a single given direction, pressure is a scalar quantity, and it hence acts equally in all directions. In SI units, the unit of force is newtons, and the unit of area is meters squared. According to the formula, pressure is equal to force divided by area. Therefore, the unit of pressure is newtons per meter squared, which is also known as Pascal, and written as PA. Notice that pressure has the same units as stress, which we saw earlier. Click on the shown link to review that section on stress. In English units, pressure is usually measured in units of pounds per square inch, or PSI. 1 PSI is equal to 6,894.757 Pascal. Another common unit that is used for measuring pressure is atmospheres, which is the standard atmospheric pressure at sea level. 1 atmosphere is equal to 101,325 Pascal, or about 101 kilopascal. A space station has a round hatch that opens to outer space. The diameter of the hatch is half a meter, and the pressure within the space station is equal to 1 atmosphere. Calculate the value in newtons and direction of the force due to pressure that is acting on the hatch. As discussed before, the pressure is equal to the force per unit area, or the total force divided by the total area. In the case of an area that is acted upon by a given pressure from both sides, we can write the equation for the difference in pressure between the two sides of the area as equal to the total force acting on the hatch divided by the total area. By rearranging this equation, we can get the total force acting on an area that is subjected to uniform pressure loads on both sides, as F is equal to the difference between the inside pressure and the outside pressure times the total area A. The surface area of the round hatch is simply equal to pi times the diameter of the hatch, d squared, divided by 4. Substituting the value of the diameter d into the equation, we get a surface area of 0.19635 meters squared. The pressure inside the space station is equal to 1 atmosphere or 101,325 Pascal. In the vacuum of outer space the pressure is equal to 0, taking the positive direction to be from the inside of the space station, pointing outwards. The total force acting on the hatch is equal to the difference between the inside pressure and the outside pressure times the surface area of the hatch. Now let's substitute the values of the variables. For the inside pressure, the outside pressure, and for the area, in the force equation, we get a total force of 19,895 newtons, or 19.895 kilonewtons. To put things into perspective, the force that was found to be acting on a half-a-meter diameter hatch of the space station, is equivalent to the force required to lift a mass of about 2 tons from the surface of the Earth. This force can be reduced considerably by setting the pressure inside the space station to a fraction of an atmosphere instead of 1 atmosphere. Similarly, in airplanes, the ambient atmospheric pressure that the airplane is subjected to decreases with altitude. This is why the pilot reduces the cabin pressure as the airplane ascends. He does this to reduce the stresses on the airplane's passenger compartment, which is caused by the pressure differential between the pressure inside the airplane's cabin and the ambient atmospheric pressure outside of the airplane. Consider 2 perfectly smooth cubic-shaped blocks. Their side lengths are equal to 5 centimeters. 4 of their faces are perfectly aligned. Assume that no air gap exists at the interface between the blocks. What is the maximum weight of the bottom block that would allow it to be lifted using the top block? The area of the mating surface between the 2 cubes is equal to the side length squared, which gives an area of 2.5 times 10 to the power negative 3 meters squared. Since the 2 mating surfaces of the cubes are perfectly smooth with no air gap between them, the pressure between the 2 cubes is equal to 0. Hence it is atmospheric pressure that keeps the cubes pressed against each other. The force due to the atmospheric pressure that is acting on the cubes is equal to the atmospheric pressure times the mating surface area between the 2 cubes. Substituting 101,325 for the atmospheric pressure and the value of the area obtained previously, we get a force F equal to 253.3125 newtons. The maximum mass of the bottom block that would allow it to be lifted by the top block can be obtained by dividing the force F by the gravitational acceleration g, which gives a mass of 25.822 kilograms. In order to obtain the pressure within a given incompressible liquid as a function of the position within that liquid, we need to consider the forces that are acting on a thin volume of that liquid, which has a cylindrical cross-section, and is contained within the bulk of the liquid. The thin liquid volume has dy as its thickness, and its top surface is parallel to the free surface of the liquid. The surface areas of each of the 2 horizontal faces of the thin liquid volume are equal to A. Since the cylindrical-shaped volume of liquid is at rest, the forces acting on it are in equilibrium. In the horizontal direction, the force due to pressure is the only force acting on the liquid volume. Since the liquid volume is in equilibrium, the net horizontal force acting on the liquid volume is equal to 0. In the vertical direction, we take the positive y direction to be pointing downwards. Hence y increases as the depth within the liquid increases. The pressure force that acts on the top surface of the liquid volume is equal to the pressure at the top surface, P, times the surface area A. This force acts vertically downwards. The pressure force that acts on the bottom surface of the liquid volume is equal to the pressure P that acts on the top surface, plus the difference in pressure between the bottom and the top surface, dP times the surface area A. This force acts vertically upwards. The force due to the weight of the cylindrical liquid volume acts vertically downwards, and is equal to the liquid's density, ρ, times the gravitational acceleration, g, times the surface area, A, of the liquid volume, times the thickness dy of the liquid volume. In the previous section, we found the forces that are acting on an arbitrary cylindrical liquid volume that is within the bulk of a liquid container. Since this cylindrical volume is at rest, the net force acting on it in the vertical direction has to be equal to 0. Hence the sum of the forces that are acting in the y direction is equal to 0. Now let's add the forces that are acting on the cylindrical liquid volume in the y direction, keeping in mind that the positive y direction is pointing downwards. And we get P8 minus P plus dPA plus rho g of dy is equal to 0. We then expand and simplify the resulting expression. What we end up with is that the change in pressure divided by the change in depth is equal to the density of the liquid times the gravitational acceleration. We can then integrate the obtained expression. We set the integration limits for the depth within the fluid as 0 and h. We also set the first integration limits for the pressure as P0, which is the pressure at the surface of the liquid, or at y equals to 0. We also set the second integration limits for the pressure as P, which is the pressure within the liquid, at a depth h. We then integrate the expression, and substitute the integration limits values. We can then simplify the resulting expression to obtain that the pressure P at any point within the stationary liquid is equal to the pressure at the surface, or P0, plus the density of the liquid, times the gravitational acceleration, times the depth within the liquid. From the expression that we obtained in the previous section, P equals P0 plus rho gh, we conclude that the pressure within an incompressible stationary liquid that is placed within a certain gravitational field depends only on the pressure that is acting on the surface of the liquid, the depth within the liquid, and the density of the liquid. Hence, if the shown three containers are filled to the same depth with the same fluid, and subjected to the same ambient pressure, then the pressure at the bottom of each of the three containers would be the same regardless of the shape of the container. Another practical consequence of the expression that we derived for the pressure in a liquid is that if we use any liquid to fill a given container that has a number of different branches within which the liquid can rise, the end height within each of these branches would always be equal if they are all subjected to the same ambient pressure. This is due to the fact that the pressure at any arbitrary point within the container has to be the same, no matter which branch we calculate the depth of the fluid from. Hence figure A on the left is correct, because the level is the same for all three branches. On the other hand, the condition shown in figure B on the right would never practically occur, since the liquid will always tend to flow from the branch that is at a higher level to the branches that are at a lower level, until equilibrium is reached. Remember that in the previous section, we said that the end height within each of the branches in a given container of stationary liquid would always be equal if all the branches are subjected to the same ambient pressure. Hence, if P1 and P2 are equal, then the height of the liquid within both branches of the shown container will also be the same. Now, what if one of the branches is at a different pressure than the other one? Consider the case where we plug branch 1 of the shown container and pump air into it, using a manual pump. As the pressure in branch 1 or P1 increases, the liquid level drops in branch 1 and rises in branch 2. This ensures that the pressure at point Q is the same, whether we measure it starting from the surface of branch 1, or starting from the surface of branch 2. In this case, since P2 is constant and equal to the atmospheric pressure, H2 must increase as P1 increases. Furthermore, as H2 increases, H1 must decrease to conserve the volume of fluid within the container. The final height difference between the two branches, delta H, is equal to P1 minus P2, divided by the density of the liquid, times the gravitational acceleration. If we were to remove the plug from branch 1, P1 would become equal to P2. This would cause the pressure difference in the height difference equation to be equal to 0, which would result in a zero value for the height difference.